Have you ever really thought about how an X-ray works? I mean, how it actually sees through you. Well, today we're going to shrink down to the atomic level. We're going to follow a single particle of light on an incredible journey through the human body to find out exactly how those images get made.
So that's the big question, isn't it? How can a beam of invisible energy see right through something as solid as bone? It feels like magic, but I promise you it's pure physics. And to solve this mystery, we're going to follow the quest of one single tiny hero. All right, let's meet our hero, the X-ray photon. It's just a tiny little packet of energy, a single particle of light. And its mission, should it choose to accept it, is to travel from the X-ray machine, go straight through a patient, and land on a detector on the other side. But, as we're about to see, it is not going to be an easy trip. That's because the human body isn't just empty space, right? It's a really dense obstacle course. And as the beam of photons travels through, it gets weaker and weaker. This process has a name. It's called attenuation. And it's the absolute key to everything we're talking about today. The beam gets reduced in intensity as it interacts with all the atoms in its path. Okay, so our little photon hero is now entering this obstacle course. And as it starts bumping into the atoms in the body, it faces a choice. In fact, every single photon in that entire beam is going to meet one of three possible fates. So fate number one, it could be transmitted. This is the easy path, right? It just zips straight through without hitting a thing. Fate number two, it could be absorbed. Bam! It collides with an atom, its journey is over, and all its energy gets transferred. And finally, number three, it could be scattered. It gets bumped, knocked off its original course, and continues on, but in a totally new direction. These three outcomes, and only these three, are what create the final image. Let's dig into the first challenge our photon might face. The most common interaction by far is something called the Compton collision or Compton scatter. The easiest way to think about it is like a cosmic game of billiards. It's basically just a glancing blow. So here's how it works. Our incoming photon comes in and strikes a loosely bound electron way out on the outer shell of an atom. That electron absorbs some of the energy and gets knocked away. But, and this is the important part, our photon survives. It's just a little bit weaker now, and it's been scattered or deflected into a brand new direction. It's still moving, but it's way off its original path. Now, what makes a Compton scatter more likely? Well, it's mostly about the physical density of the tissue, how tightly packed the atoms are. But here's the crucial point, the thing you have to remember. It doesn't really matter what kind of atom it hits. This means Compton scatter happens pretty much equally in both soft tissue and in bone. It's happening everywhere.
But wait a second. If Compton happens everywhere, how do we get a clear image of anything? Well, that brings us to let's call it the final boss of interactions, the photoelectric knockout. This is the all-or-nothing showdown that truly forges the X-ray image we're familiar with. Now, this one is way more dramatic. An X-ray photon comes in and strikes a tightly bound electron, one that's in an inner shell. And instead of a glancing blow, the photon transfers all of its energy to that electron. The photon completely vanishes. Poof, it ceases to exist. It gets totally absorbed, sacrificing itself just to knock that one electron out of its orbit.
So when is this dramatic knockout most likely to happen? Well, the probability is highest when the photon's energy is just a little bit more than the energy holding that electron in place. It's kind of like having the perfect key for a very specific lock. If the energy is just right, that absorption is almost guaranteed to happen. So now we've got these two main events, Compton scatter, that glancing blow that happens all over the place, and the photoelectric knockout, that super specific all-or-nothing absorption. So the big question is, which interaction wins? Which one is actually more important for the image we see?
And the answer to that question comes down to one single critical property of whatever our photon is trying to get through. Its atomic number, which we usually just call Z. This table just lays out the difference perfectly. Just look at the depends on row. Compton scatter is all about density, but the photoelectric effect is highly dependent on the atomic number. And that right there is the whole secret. This is why Compton is the main event in soft tissue, while the photoelectric effect completely takes over in materials like bone. Okay, so we've been following our one little photon. Let's zoom out now. A real X-ray isn't one photon, it's billions of them. And it's the collective result of all their individual journeys, all those transmissions and scatters and absorptions, that forges the final image that we actually see. And here's the most crucial point of all. An X-ray image is basically a shadow map. It's a map of where photons were stopped and couldn't reach the detector. The bright white areas you see on an X-ray, that isn't where light is shining on something. Those are the shadows where the light was blocked. And this chart shows us exactly where that blocking is happening the most. It's pretty clear, right? Bone stops way more X-ray photons than soft tissue does. That means bone is casting a much, much bigger photon shadow.
And here's the final piece of the puzzle, the why. Let's connect it all back. Your soft tissue, it's made of elements with low atomic numbers, so not a lot of photoelectric absorption happens there. Most photons pass right through, hit the detector, and make that part of the image look dark. But bone? Bone is full of calcium, which has a much higher atomic number. This causes a massive increase in photoelectric absorption. Far fewer photons make it through, and that creates that bright white shadow on the final image.
So let's just recap real quick. X-ray images are created by attenuation. The two key interactions are Compton scatter, which happens everywhere, and photoelectric absorption. And that photoelectric absorption is the real secret to contrast because it dominates in materials with high atomic numbers, like bone. That difference in absorption, that is the image. Which leaves us with one last really interesting question. If the whole trick of the photoelectric effect is that it lets us see things with high atomic numbers, how could we possibly use that exact same principle to make things with low atomic numbers, like blood vessels, suddenly show up bright and clear on an X-ray? Think about that for a second. The answer is actually the basis for a whole other incredible area of radiology. Thanks for joining me.